So as we discuss polar covalent bonds and uneven sharing of electrons, you may wonder, how do we know which elements prefer to pull on electrons harder, or have a preference for electrons to be near those particular atoms? And the scale we use to understand this is what we call electronegativity. And this is a property of atoms that has periodic trends similar to ones that we've observed before for ionization energy. And so this periodic table I have laid out here has the values of electronegativity for different elements in the periodic table. So the scale runs, our very smallest values down here in the bottom left corner for francium and cesium are about 0.7, and fluorine has definitely the very largest electronegativity of about 4. So the higher the electronegativity, we'll abbreviate it as En, higher En means the more the atom pulls on electrons. And so in a polar covalent bond, whatever has the higher electronegativity is going to be the negative side of that bond. So that's what's going to turn into our negative side. So in general, our elements that are near the top right of the periodic table, in particular the ones that are going to tend to make very polar covalent bonds, are fluorine, oxygen, and then nitrogen and chlorine are up there pretty high as well. As you can see, the trends here basically follow the same trends that we see for atomic size, and the reasons are the same. As we go left to right across the periodic table, the effective nuclear charge increases, and that's why these atoms pull on electrons with more force, and so why their electronegativities are higher. And as we go down the periodic table, the electrons are further away from the nucleus. We have more core electrons that are shielding those electrons on the outside, and so they pull a little bit less on the atoms. And the other thing you probably noticed is that all of our metals here down at the bottom all sort of share the property that they have very small electronegativities. Most of them would rather give up electrons than gain electrons. And so when we're looking at bonds, it's really this difference in electronegativity that matters to tell us what type of bond we have. If two elements have a very similar electronegativity, so say you have two of the same element, like our Cl2 example that we were looking at earlier, there the difference in electronegativity, or delta En, is 0. There is no difference in electronegativity because they're the same element. And so we get equal sharing of electrons. Now, we can have things that are not the same element, but still have very small differences in electronegativity. So say we're looking at something like carbon and sulfur. So carbon right here, sulfur right here, they have the same value of electronegativity. And so if we were looking at something like carbon disulfide CS2, the Lewis structure looks like this. You can go through and double check, go through the steps to double check for yourself. But each of these bonds here would be very nonpolar, what we call nonpolar, meaning that the electrons are very equally shared. On the other hand, things with very large differences in electronegativity if the difference is very, very large, then it's likely going to form an ionic compound. So that's why when we combine things like sodium with chlorine, we have a very large difference in electronegativity, something on the order of about 2. Sodium is about 1.9, whereas chlorine is about 3. So anything, the rough scale is, let me just pull over this figure that has this. The rough scale is that anything greater than about a difference in electronegativity of 2 will be ionic. Between about 0.5 and 2 will be about polar covalent, and then our nonpolar, like our carbon, sulfur, or Cl2 here, those would be our nonpolar that have a very small difference in electronegativity. So this scale helps us to make sense of why we see why we see these polar covalent bonds, and take this with a grain. This chart here is approximate, right? So the details matter here, like how heavy are the atoms and things like that, but gives you a rough guide as to whether you expect a bond to be polar or nonpolar. And that concludes our discussion of electronegativity.